Hey guys, what's up? What's going on? My name is Shanto, and today I'll be showing you guys how to solve the longest increasing subsequence problem. This is problem 300 on Leetcode, and it's another very common problem that will help demonstrate your knowledge and test your knowledge in dynamic programming. And dynamic programming should give you the hint that we're either going to be utilizing memoization or tabulation. Um, I usually go for tabulation because I think that's just what I'm used to now. So we'll be using tabulation to solve this problem. But first, let's go over what the problem is. So we're given a longest increasing subsequence. We're given, cut that out. Okay, so let's go over what the problem is. We're given an array, right? So in this example, I'll use example 1 as my example as well. We're given an array, 10, 9, 2, 5, 3, 7, 101, and 18. And what we have to do is find the longest increasing subsequence. And what you have to note that in this problem, and they specify in this sentence here, is that a subsequence is a bunch of numbers where one comes after the other in the array, but not strictly right after the other. So for example, 0316227 is the array that they're giving us. An example subsequence in this array is 3, 6, 2, and 7. 3, 6, 2, and 7. And you might be like, oh, that's weird. You're skipping this 1 here, or you're skipping one of these 2's here. But in their definition, they're not saying that the subsequence has to be like right next to each other. They're saying the subsequence is just numbers that are after each other in the array at all. There can be numbers in between as long as it's after. So with that in mind, and with the constraints in mind that there's always going to be some number in the array, since we're using tabulation as our strategy here, we have to make a new array. The strategy is to make a new array that has the number of slots that is the length of the array, right? So I have my iPad here. So let me bring that up. And what we're going to be doing is we're going to make an array that is equal to an array that has a length that's equal to the length of the given array, right? So in this example where we're given 10, 9, 2, 5, 3, 7, 101, and 18. Sorry guys, I've got like 4 hours of sleep last night. God knows why. So we're given this array, and to solve the problem, like just looking at it, what is the longest strictly increasing subsequence? Well, given that you don't need the numbers to be right next to each other, there's this 2 here, then it goes 2, 5 is bigger than 2, then 7 is bigger than 5, and then 101 is bigger than 2. I mean, also 18 is bigger than 2, but like that's not the point. The point is that it could be the largest subsequence. So I would say the output is 4, right? This is going to be our output. So given this input, our expected output is 4. Yeah. So how are we going to do this? Like I mentioned, we're going to make an array that is keeping track of the longest subsequence up to that point for each of these numbers, right? So we're going to make an array that represents the longest, where each element represents the longest subsequence up to that point for each of these numbers. So in order to do that, we have to make an array that has a length equal to this array's length. So let's just do that here. This is 1, 2, 3, 4, 5, 6, 7, 8. So let's make an array 1, 2, 3, 4, 5, 6, 7, 8. Right? So this would represent 10, this would represent 9, this would represent 2, this would represent 5, this would represent 3, 7, 101, and 18. Yeah. Awesome. And what are we going to store in here? We're going to store the longest subsequence up to that point. And what is the shortest subsequence that we could possibly output ever, given the fact that there's always going to be a number in the array, and that's a constraint that they gave here. It's going to be 1. So it's pretty safe to fill this all with 1s as we initialize the array. And then we're going to, iterate through and fill it in with the actual numbers. And how are we going to do this? What we're going to do is we're going to have a pointer. And this pointer is going to iterate through the array, and as it iterates through the array, it's going to compare that number. It's going to compare the number in the given array to the numbers before it. And it's going to say like, oh, is this increasing from that point or is it not? And if it's increasing to that point, is it increasing? If we were to add 1, will that increase the longest subsequence or not? Or are we already the longest subsequence? This will make more sense when we code it out and when I explain it in a second. So let's go through an example, right? So this pointer starts at the beginning of the array, but it's the beginning of the array. So that's the longest subsequence up to that point is 1. Then we move the pointer to 9. We're going to compare this to the number preceding it, right? All numbers preceding it. In this case, there's only 1. Is 9 greater than 10? No. So the longest subsequence up to this point is still just 1. 2. Is 2, where the pointer is now at 2. Is 2 greater than 9? No. Is 2 greater than 10? No. So it's still just 1. 5. Now this is the first one where we actually have a greater subsequence, right? So we're going to say, is 5 greater than 10? No. Is 5 greater than 9? No. But is 5 greater than 2? Yes, it is. Now what we have to do is compare this 5, right? 5, we're going to compare it to this number, and we're going to say, yeah, it's greater. But then we have to do another comparison. We're going to say, if we were to increase this number by 1, if we were going to increase this number by 1 and say like, yeah, increasing the subsequence by 1 at this point would make it bigger than the subsequence already that I have stored in the slot, then we're going to save that. And if not, then we're just going to stick with what we already got. In this case, it would, because if I were to add 1 to this 2, then the output would be 2, and 2 is greater than 1. So we're going to slot here with 2, because the greatest subsequence up to this point right now is 2. It's this 2 and 5. Great. So then we're done with the iteration on 5. Now we're going to move the pointer to 3. Is 3 greater than 10? No. Is it greater than 9? No. Is it greater than 2? Yes. And would increasing the subsequence by 1 at 2 be greater than this 1? Well, 1 plus 1 is 2, and that's greater than 1, so yeah. Is 3 greater than 5? No, it's not. Let's move the pointer over to 7. 7 greater than 10? No. 9? No. 2? Yes. Now let's look at this slot, right? Is 1 plus 1 greater than the current 1 at this 7 slot? Yes, it is. So let's slot this at 2. Is 7 greater than 5? Yes, it is. Is 1 plus whatever is slotted at 5 greater than our current subsequence slotted at 7? Yes, it is, because 3 is greater than 2. Oops, sorry. 3. Now, here's where that second comparison really is important. Is 7 greater than 3? Yes, it is. But if we were to add 1 to this 3, whatever's slotted at 3, if we're going to add 1 to that subsequence slotted at 3, is that greater than what is currently slotted here? Well, 2 plus 1 would be 3. And 3 is not greater than 3. So this is going to remain 3, right? Now, let's move on. Our pointer is now at 101. Is 101 greater than 10? Well, yes, it is. And if we were to add 101 to the subsequence at 10, then we're at 2, because 2 is greater than the one that was already slotted at 101, right? So is 101 greater than 9? Yes, it is. But this is going to remain 2 because 1 plus whatever is slotted at 9, 1 is still 2. Is 101 greater than 2? Yes, but same case. 1 plus 1 that's slotted at 2 is still 2 that we have here, so nothing's going to change. Is 101 greater than 5? Yes, but it's different in this case because 2 plus 1 is greater than the 2 that is currently slotted at 101. So this is going to be 3 now, right? Is 101 greater than 3? Yes, it is, but it's the same case. 2 plus 1, because 2 is currently slotted at 3. 2 plus 1 is still 3, so this is not going to change. Now, is 101 greater than 7? Yes, it is. And the current longest subsequence at 7 is 3. So if we were to add 101 onto that subsequence, this 3 would be a 4. And 4 is greater than the subsequence we currently have stored as the longest at 101. Yep, you get the idea. And then we only have one left, so let's just go through it. Is 18 greater than 10? Yes. Now, what do we check now? If 18 is greater than 10, then we have to check, would adding to this subsequence, the subsequence stored at 1, would adding that make the current subsequence stored at 18 longer? Yeah, it would, because 2 is greater than 1. You get the idea, so I'm going to go really quick now. Is 18 greater than 9? Yes, but it's not going to do anything if you add. Is 18 greater than 2? Yes, but not going to do anything if you add. 18 greater than 5? Yes, it will do something if you add it. Is 18 greater than 3? Yes, but nothing's going to change if you add on to the current slotted number of 3. Is 18 greater than 7? Yes, and it will actually add on if you add 18 to the current longest subsequence that's running at 7. And then 18 is not greater than 101, so there's no comparison to make there. Okay, cool. So that's the strategy. Let's code it out. And again, I think I'll probably draw out what I'm doing as I'm coding it. So remember, the first thing that we need to do is, given this input, I'm going to just do this again. Given the input 10, 9, 2, 5, 3, 7, 101, and 18. Given this input, we have to make an array with the same number of elements as this given array. 1, 2, 3, 4, 5, 6, 7, 8. Okay? And like we discussed earlier, we can sort of pre-fill these with 1s, because that's going to be the minimum value at any point. Okay, how do you do that in code? Quite simple. Let's name this array DP array because it's a dynamic programming problem, dynamic programming array. And this is going to be an array that has, again, 4 hours of sleep. This array has a length that is the length of the given array. So nums.length, and we're pre-filling the values all as 1, right? Cool, that's awesome. Now, what are we going to do? Well, we have to set up our pointer, right? We have to set up our pointer that's going to move through this array. Yeah? So let's set up a pointer that moves through this full array. So we're going to say .each, and we're going to name that pointer I. Now, we have the pointer that's moving through the array, right? So if I were 0, 1, 2, 3, it would be here. This is the I pointer. And remember, what do? We're comparing this I pointer to the numbers preceding it, right? We're comparing it to the numbers preceding it. So let's make a second pointer, 0, all the way up to the pointer that we're currently on, the original pointer. And we're going to call that J. And then remember, what's the first check? So if this number here is representing this 5, and this number here is 10, then the first thing we have to do is check, is 5 greater than 10? Right? And that's some conditional logic. Is 5, which is represented at nums of I, the original pointer, is that greater than 10, which is nums at j, the second pointer that we set up? If it is greater, in this case it's not, but let's use a different example, right? So instead of 5, let's say we're using 3 and the 2 here. So let's say we were comparing, let's say I is at 3, right? And our j is at 2. So we're comparing 3 to 2, in which case nums at I would be greater than nums at j. Then what do we have to do? We have to compare. If we were to extend this longest subsequence that's stored at 2 by 1, would that be greater than our current longest subsequence that's already stored at 3? Right? And how do you compare that? You could do some if then, but since we have to choose whichever is greater, right? Is it what's already stored at this slot, or is it what's stored at the previous slot that I'm currently comparing myself to plus 1? And so if you're making a comparison like that and storing that comparison in this slot, we can do a dot max, right? So dp array at this slot where my pointer is, the original pointer, dp array, we're going to store that value as whatever is bigger between whatever is currently stored in this slot and between the slot that we're comparing ourselves to plus 1, because we're extending ourselves by 1. And if we're comparing and selecting the biggest value, then we're doing dot max. Let's end out our loops. And then in the end, we have, like we have this array. This is what it would look like once it goes through and iterates. In the end, we just have to select the longest subsequence that we found, which would be like, this one or this one, 4, right? And that's the output that we expected, 4. So we can select it by returning dparray.max. And that's it. So what you have to keep in mind is that this is actually an O of n squared solution, because we're iterating through the elements, and then we're iterating through all the elements preceding each element. So this is going to be O of n squared, but there is a way to do it in O n log n time, as they say down here, O n log n. But I mean, it seems that you would not be expected to just like solve it that way. Like this strategy here is the general strategy that you would be expected to go through to solve this problem. The O n log n time solution is very hard to get to, and I don't think anyone would be expecting that of you. So although this is not technically the optimal solution, the most efficient solution, it's probably the best one for you to learn the strategy of dynamic programming. So let's submit this and see if it works. Cool, it does. And like I said, it's not the most optimal solution, but it's probably the expected one. And like I showed in my last video, this number can change depending on how Leetcode feels, right? I actually don't know what drives that number because I'm an idiot, but yeah. So that is, see, like same exact code, but time limit exceeded this time. That's whack, yo. Totally whack. Yeah, dude, I don't know. It like, you see, like I use the same solution basically for all of these, and they are so drastically different. Anyway. Yeah, 4 hours of sleep. I'm sorry. Okay. That's my solution. And I'll see you guys later. Thanks for watching. Bye.